Hello everyone, welcome to the Spintangle. This is the lecture 15 of statistical mechanics. Okay, lecture 15 of statistical mechanics. In this lecture, we will be discussing on canonical ensemble statistics. Okay, canonical ensemble statistics. In case of classical ideal gas. Okay, and therefore we will be moving on our next topic. This is our first topic that we will be discussing the classical ideal gas in case of canonical ensemble statistics, and secondly we will move into the application part. Okay, this is the application part of this thing, so the problems related. Okay, application part, this will be more interesting. Okay, this will be more interesting to you, so let's move on to the classical ideal gas. Classical ideal gas. Okay, so say a classical ideal gas is what the gas which is a continuous phase-space trajectory. Okay, and also there will be the particles obeying Maxwell-Boltzmann statistics. In case of the particles obeying Maxwell-Boltzmann statistics, we use classical theory. Okay, it means classical. That means the particles are distinguishable and their wave function are distinct. That means no overlapping wave functions are there. Okay, so that's why let me write something here. Let us consider. I'm writing here it. You can write this thing out. Okay. Let us consider a classical ideal gas containing n particles that are non-interacting. Say they are monoatomic. Okay, monoatomic, non-relativistic. They are non-relativistic and indistinguishable. Okay, we are considering them indistinguishable. Okay, indistinguishable. Just wait. And I am not writing more thing here. So from the system you can easily see that there are total number of particles is n and the total volume is v here. Okay, here I am elaborating each and every term from this thing. Okay, let me change the ink here. So n particles are non-interacting. The first term is here is non-interacting. Okay, what are the non-interacting particles? Say this non-interacting particles. Non-interacting particles means the particles which are free from the influence of other particles. That means they are not interacting. Say this is a particle. Say this is a particle. This particle, if this is one single isolated particle, therefore it will create a potential. Okay, therefore it will create a potential. Say I'm giving the potential like this. Say this is the potential, okay, this is the field, this is the field of this particle, or this is the area of this particle in which the particle is active, okay. Therefore this is the particle in which another particle, if another particle comes, then it will feel some interaction, okay. Say there comes another particle, okay, it will feel interaction, feel a force, okay. this is the this is the this is the particle called non-interacting, okay. Non-interacting means if this particle do not feel any kind of potential caused by this particle, okay. If this particle do not feel any potential which has been created by this particle, okay, that means this particle it will not feel anything, okay. That means the interaction potential will be what? That means interaction potential will be, I am writing this thing out, say the interacting potential, interaction potential will be 0. That means this thing is not interacting with this thing, okay. This thing is not influenced by the potential created by this thing, okay. So next point is what? The particles are classical particle. Classical particle means what? Monoatomic. You know what monoatomic, non-relativistic means. You can easily calculate its energy by putting E is equals to half mv square. The kinetic energy is equals to half mv square, okay. That means plus V is the potential and so on, okay. So easily what we can see, the interaction potential is what? 0. That means we can write this particle is free, okay. That means this particle is free. Free means what is the potential of this thing? The potential of this thing will be 0. That means the total energy will be what? The total energy of the particle will be what? Energy will be given as, say, E is equals to what I have did the above, okay. That is kinetic energy plus potential energy. This means what is the kinetic energy of a non-relativistic particle? That means half mv square. In case of relativity, you are allowed to do this thing, okay. This is the p square c square plus m0 square c to the power 4. I think it is correct, okay. This is the relativistic energy term, this is the non-relativistic energy term, okay. These are all, this is the kinetic energy in case of relativistic particles. And now, as I am not considering the particle as a relativistic particle, that means the particle is non-relativistic particles. In case of non-relativistic particle, the kinetic energy is half mv square, as you know from your earlier classes. And now the potential energy is what? Potential energy in our case will be 0. That means what we can write from this thing, that E is equals to half mv square. That means this thing, okay. This means you can easily construct this thing, say m square v square upon 2m. You can write this thing as m square v square upon 2m. That means what does it become? It becomes p square upon 2m, okay. That means from the now I'm moving to the to another point, the monoatomic particle, okay. The monoatomic particle, monoatomic particle, indistinguishable particle, these are the clear thing to you, I think so. It's a monoatomic particle. Monoatomic particle means monoatomic free particles. This particle potential energy is what? In case of this thing, potential energy is 0. That means the particle is free to move from anywhere to anywhere. That means what? Monoatomic particle. And we can easily say as V is equals to 0, that means the particle is not influenced by any external potential causing from any other source. That means the number of constant will be what? K is equals to 0. As we know, the degrees of freedom formula, F is equals to dn minus K. That means what is the D here? Say the particle is in 3 dimensions, so the container is a 3D container, okay. Say the container is a 3D container, okay. I am doing this thing. These are the manipulations which has to be done in case of 3D 2D or whatever it is. This is the drawing techniques. Okay, see, monoatomic means n equals to 1 and k is equals to 0. That means degrees of freedom will be 3 here. Okay, now the thing that the single particle partition function in classical. What is the single particle partition function? You know this thing. Single particle partition function is what? Pause this video here and think about your previous lectures, from your previous lectures, that I have given the formula which has been discussed previously, that in case of single particle classical partition function, okay, single classical particle partition function, that means if the particle is classically treated, that means the partition function for a single particle is given by, say, this is q1 equals to what, 1 upon hf. Here it will be integration for, and a double integration. Here will be double integration because partition function is written in the phase space trajectory. Phase space means qp space. Okay, this is position and momentum space. So from this formula, what we can write? 1 upon hf integration is equals to e to the power minus v. E is what? E is our energy. Okay, E is, it is E, and df q and dfp. This is the general formula in case of single particle partition function. As in our case, our degree of freedom is what? F is equals to 3. F equals to 3. That means what? We need to plug them here. Okay, H equals to plug it. Okay, not them. That means e to the power minus beta times beta is what? Beta is 1 upon kt. Okay, please remember this thing. Beta is 1 upon kt. Beta. E is what? E is, we have calculated it. That means p square upon 2m is our E, and here it will be d cube q and d cube p. That means third order differentiation on position and the third order differentiation on momentum. That means now it is clear from this thing. So what we have to do here, let's divide the integration symbols to the arguments. Okay, in this case the first argument is what? The position argument. The first integration will be on what? The position, and the second integration will be on what? The momentum. That means in case of, you can easily see this is a function of momentum. Okay, for a fixed temperature, I can write this thing. This is a function. This is a function of momentum. Okay, this is a function of momentum. What you can easily write from this thing, that you can easily, you have to mention this formula when you are using the p integration. When you are using the p integration, with this integration symbol, this term will go out. That means here it will be e to the power minus beta p square upon 2m, and here will be the argument, that is dqp. Okay, this is the integration you have to solve, and after solving this thing, we will be getting a very interesting result, and you have to remember the result. Okay, that means 1 upon hq from this thing. And what is this? This is the spatial volume. Okay, that is what is this is dx dy dz. This means equals to v. Okay, so what we can obtain from the first integration, that is the volume. Okay, and from the second integration, what will be here? The second integration will be given by e to the power minus beta p square upon 2m, and here it is a p integration, that integration on the momentum. Here what you can see, that is dqp. This is what? This is the volume of the momentum space. That means volume of the momentum space, momentum annular space. We have calculated this thing. This is how to calculate the volume of this annular thing. Annular thing means, say you have a positive px, py, pz axis. This is the px axis. This is the py axis, this is the pz. I have calculated this thing in previous lectures. Okay, so in case of there is an internal sphere, this is a portion 1/8 portion of the internal sphere, and there is a external sphere. Okay, this is also the 1/8 portion of the external sphere. Both sphere has different radii. That means you have an annular space, you have an annular space. The volume of this annular space will be given by, say, the radius is p. This means d cube p will be what? The volume of the annular space will be 4 pi p square, that is the area of the internal sphere times the thickness of this annular region. Okay, this is the annular region. Okay, that means what? You have to plug this thing here. That means, let me change the ink. So from this thing you have to put this thing 4 pi p square dp. Okay, I think I am correct. That means it becomes v upon h cube. Here it is p. Here it is. You can easily write this thing. I have 4 pi opt out this 4 pi from the integration, and what does it become? It becomes 4 pi v upon h cube integration. Okay, you may put the limit from the concept of momentum, that a particle uh, at rest has momentum is what? 0, and there will be no negative momentum, that therefore the minimum value of momentum is 0 and the maximum value of momentum is what? Infinity. When the value of momentum will be infinity? When the energy will be infinity. That means in case of very high temperature. Okay, 0 to infinity, you can write this thing as p square e to the power minus beta upon 2m. Here it is p square, here it is dp. Okay, now you have to solve this thing, and there is a standard formula of solving this integration, as I have given this formula on the offline class. And the offline class, this formula is written as, I think so, say x to the power, say this is the general formula, that in case of this kind of integrations you have to, this is a very interesting integration, that x to the power m e to the power minus alpha x to the power n, here it is a dx. That means the answer will be what? 1 upon n gamma function of m plus 1 upon n. This is the gamma, this is gamma. Okay, this is gamma. Okay, here it is alpha to the power m plus 1 upon m. Therefore you have to solve this thing from this thing, that 4 5 v upon h cube, and here it is. What will be the value of this thing? Calculate this thing. What is m here? This is the m. Okay, this is the m. What is n here? This is the n. And what is alpha here? This is the beta upon 2m is the alpha. They plug them in this formula, that 1 by n. This means 1 upon 2 is being, and there will be extra terms. Just let me check this out. Okay, half, and there will be a m plus 1 upon n. That means gamma m is what? 2 plus 1 upon 2. I think I'm correct. Okay, that means in the denominator you have this value, that beta upon 2m whole power 2 plus 1 upon 2. I mean, this is the ultimate thing. Okay, okay, now what we have to do? 4 pi v upon h cube, and solve this thing out. Okay, this is the half, and this is the gamma function. This is gamma 3 by 2. This is gamma 3 by 2. Gamma 3 by 2 is what? Gamma 3 by 2 is, you can write this thing as 1 plus half. Okay, 1 plus half is 3 by 2. That means what is the value of 1 plus half gamma? That means half gamma half. That means what is the value of gamma half? I think it is root pi. I think it is root pi. Okay, this is half root pi, the value of this thing. But this means there will be a 1 upon, there will be another half root pi, and sorry, am I correct here? This is 1 plus half. This is half gamma half. Let me check it before after after the calculation. Okay. So and in the denominator you have 1 upon, calculate by it your own. Okay, so I am putting the value of beta from this thing, therefore it will become 2m kt to the power 3 by 2. And the beta, what is beta? Beta is 1 upon kt. Okay, this is 1 upon kt, where k is the Boltzmann constant. That means from this formula you have this 2 goes with this 4, and this pi and this pi becomes pi to the power 3 by 2. I think it is pi to the power 3 by 2, and here it is a v upon h cube. And then this thing, this will flip, and this will another time this will flip. Okay, this will flip to the numerator. Okay, this means it becomes 2 mkt to the power 3 by 2. 3 by 2. Okay, we check this thing out. Okay, so what you can do from this thing, that you can easily see this thing out, that the pi having a power of 3 by 2, and it will goes with this thing. Okay, that means v by h cube upon, you can easily write this thing 2 pi mkt to the power 3 by 2. This is what? This is the single particle partition function. This is, I am writing as single particle partition SPPF. Okay, what will be the many particle partition function from this thing? Okay, what is the many particle partition function? Before going to the many particle partition function, remember this formula. Remember this formula each and every time whenever you are going to do a problem or whatever it is. In case of your throughout the lifetime, you have to remember this formula for classical ideal gas in canonical ensemble. I am writing this thing. From where it is come? It is coming from this, the classical ideal gas in canonical ensemble. Okay, so this is the single particle partition function. So for now you have to know about a thing, what is a quantum mechanical approach, the thermal de Broglie. I am not going more elaborate on this thing, that thermal, what is thermal de Broglie wavelength. Okay, this is thermal de Broglie wavelength. Thermal de Broglie wavelength is what? It is written as lambda thermal, because this is the wavelength, formula of wavelength. It is h upon root over 2 pi m kt. Okay, this is 2 m pi kt. Okay, whatever it is. Okay, got this thing? That means you can easily write this thing from this form, squaring the lambda thermal, squaring the lambda. This is the thermal de Broglie wavelength. Sometimes it is directly asked to some problems. Okay, so you must remember this thing. So before remembering this thing, you have to remember this thing specially. Okay, so I have encountered many of the problems, many of critical problems which has been asked from this formula, and the people are fumbling with this thing okay, because they do not they remember the formula. Okay, you have to remember this formula. So what we can, by squaring this thing, lambda thermal, squaring this thing, the lambda square, it here will be, and here it is, and there is the surviving term, it is only 2 pi mkt. Okay, 2 m pi kt, I am writing h square, squaring. So what you can see from this formula, that you can easily write this thing. Put the value of, so 2 pi mkt is what? 2 pi mkt is equals to h square upon lambda thermal square. Okay, this is the value of 2 pi mkt. Put this thing on our Q1 formula. Okay, what is our single particle partition function? That is Q1 is equals to V upon HQ 2 pi mkt to the power 3 by 2. Put the value of 2 pi mkt from this formula to this. Here put this thing. Here it will be V upon HQ, and here it will be H square upon lambda thermal square to the power, I think it is 3 by 2. This means it becomes V upon H cube, and here it will be, I think in the numerator it will be H cube, and in the denominator it will be a lambda thermal cube, and I think I am correct. Okay, check this thing. The Q1 becomes here they will goes with each other. Okay, so it will become that V upon lambda thermal cube. This is the single particle partition function in terms of, I am writing this is what single particle partition function in terms of thermal de Broglie wavelengths. Okay, so sometimes it is called thermal de Broglie. Okay, most of the people's call this thing the de Broglie is not the actual pronunciation. They pronounce it more perfectly, that is de Broglie, and we think it is too much bizarre to pronounce de Broglie like de Broglie. Okay, it is problem of our Indian students. Okay, this is SPPF in terms of thermal de Broglie wavelength. This is the single particle partition function. Okay, so for many particle partition function will be, for n particle partition function will be what? For n particle partition function, this will be the partition functions n given. This will be up to q1 up to what, n times, because partition function relies in a multiplicative manner. Okay, so you have to multiply this thing out to get the total result. In case of n particle partition function, it's up to n times. So what is the q1 here in our case? This means this is what, this is q1 power, and this is capital N, q1 power n. This is in case of distinguishable. This is the problem which we have encountered in case of I think in case of Gibbs paradox. Okay, so if you are not familiar with this thing, then you may go to the Gibbs paradox and go to the video of removal of Gibbs paradox, and you can easily see this thing, that this is the distinguishable partition function, distinguishable particle function, and in case of indistinguishable particle function, you have to put an extra in factorial term in the denominator. Okay, so this is the q1 is equals to q1 power n. This means what? Let me check, just wait. So q1 power, and this is in the case of distinguishable. So in case of indistinguishable particles, what will be here? In case of indistinguishable particles, you can easily see this thing from our consideration. Okay, from our initial consideration. What was our initial consideration? Our initial consideration was the particles are indistinguishable. Okay, this is the thing, the particles are indistinguishable. So we have to calculate the indistinguishable partition function. What is our indistinguishable particle function? In case of indistinguishable particle function will be given as that q1 equals to q1 power n upon n factorial. This is the thing that you have to remember in case of indistinguishable particles, that is 1 upon n factorial. What is the value of q1 power n? What is our q1 means v upon lambda thermal cube, I think I am correct, and power n, because q1 is v upon lambda thermal cube, and in the power of q1 here will be an extra n, and in the very front of the equation there is a 1 upon n factorial, a factor. Okay, so this is the indistinguishable particle case you have to remember for your problem solving approach. So let me make a conclusion from this thing, that the single particle conclusion. Okay, classical ideal gas in case of canonical ensemble, this means what, this means the single particle partition function is given as q1 equals to, what is this, phi upon h cube 2 pi mkt, this is m, 2 pi mkt power 3 by 2. Okay, in terms of thermal de Broglie wavelength, thermal de Broglie wavelength, this formula changes to, I think, v upon lambda thermal cube, this is the q1, and so on, and you can easily calculate that's q1 for distinguishable if the particles are distinguishable. For if the particles, and then n particle partition function will be what, it is q1 power n, this means p upon lambda thermal cube power n, and in case of indistinguishable particles, there will be, the function will be defined by n factorial, this means what, 1 upon n factorial, here it is phi upon lambda thermal cube to the power n, this is the arithmetic. Okay, so this is our calculation in case of classical ideal gas. So next, moving on the discussion of what is our topic, I've forgotten this thing. Okay, what is our initial topic, that application. Yes. Now we are starting the application of canonical ensemble topic. Okay, application of canonical ensemble, this is based on level systems. Okay, this is called level system. Go through the riff book and you can easily see this thing. Level system means you will be given some energy levels and you have to distribute some particles on this. Okay, this type of questions are asked in recently, you can see it in any of the competitive examinations. Okay, any of the competitive, your knowledge is required to do this thing. Okay, so how to do this thing? Level systems are asked for fermions, for bosons, and for Maxwell-Boltzmann particles. So what we have to do from this thing, I am going to the problem. Before going to the problem, I am mentioning some point, that is, first, in case of level system problems, how to deal with problems. Okay, how to deal with problems. Okay, step 1, I'm not writing step 1 here. So this is, first of all, you have to calculate the number of ways. I think you are now able to calculate the number of ways. Okay, number of ways. So number of ways, how to calculate number of ways? That in case of fermions this is a GiCni. In case of bosons there is a term Ni plus Gi minus 1 and by Ni factorial times Gi minus 1 factorial. And in case of Maxwell-Boltzmann particles there is a Gi power Ni. Okay, ways. So first of all you have to calculate the number of ways, then make diagrams and fill up particles. In the third step, calculate the total energy. Calculate the total energy. Okay, in the fourth step, what you have to do, that make a table making. I'm writing this tabulation. Okay, tabulation, and in the very last term there is a partition function. It is asked partition function. Okay, this is the I think this is the intermediate steps of calculating partition functions. Okay, so first of all you have to write the number of ways in case of calculating partition function. This is the first step what you have to do, calculating the number of ways. Then you have to make diagrams and fill up the particles, and now you have to calculate the total energy of the system for each and every case. And in the fourth step you have to do some tabulations. These are the tables of energy and internal boxes, energy and degeneracy table. And finally you have to plug this thing on the partition function formula. I think you know this thing for partition function formula. What is the partition function formula? This is equals to summation Gi e to the power minus beta ei. I think it is correct for canonical partition function. This is called canonical partition function. Okay, so let's calculate this canonical partition function. I am giving a problem. Problem is interesting problems. These are the interesting problems. Calculate the partition function in filling two bosons in the energy levels say the energy level is given as minus 2e and plus 2e. Okay, in which the first two levels, this is an interesting question, I think. Levels are non-degenerate and the last energy level is doubly degenerate. The last two energy levels is doubly degenerate. Okay, so what we have to do, read the question carefully, that calculate the partition function in filling three bosons. Okay, calculate the partition function in filling two bosons. There are two bosons. Say you have two bosons. Okay, in the energy levels minus 2e plus e plus 2e. Okay, in which the first two levels are non-degenerate. Okay, that means the minus 2e and plus e, these are the two energy levels. These are the two energy levels which are non-degenerate, and this is degenerate. How much degeneracy? It has degeneracy 2. This means it will split up in further 2 steps. Okay, this is the question. So make the, first of all, what you have to do, you have to say I'm doing the first, I'm writing the energy level diagram. First make the energy level diagram. How to make energy level diagram? That you have a level, you have just wait, you have a level minus 2e, and the second level is plus e, and the third level is plus 2e. This means you have to fill up these two bosons in these 3 states. Okay, this is the criteria of what we have to do. Okay, this is the energy level diagram. So you have to fill up these 2 bosons in these 3 energy levels. Okay, in this case what we have to do, in case of bosons, we know these are the 2 bosons, this is the number, this is n. Okay, this is the ni is what? Ni is 2. That means there are 2 bosons. Okay, and there are 3 energy levels, in which you have to think about that this is given. You have to split this thing. This is non-degenerate, this energy, this means this is a single energy state. Okay, this is a single energy state, in which there will be wave functions having single energy. Okay, it's a single wave function, there will be a single wave function, and there will be in the 2e state, you can easily check this thing from the question, that the last energy level is doubly degenerate. That means you have to make this thing, okay, that the energy level is split in 2 further energy levels. Okay. This is the degeneracy. Okay, so now how many chambers now we have? How many chambers? That means how many branches? This is a branch, this is a branch, this is a branch, this is a branch. You have 4 branches now. Okay, that means gi will be what? Gi will be 4. Okay, as these particles are bosons, therefore the number of ways will be what? Number of ways in this case will be omega equals to ni plus gi minus 1 factorial upon ni factorial into gi minus 1 factorial. Now plug this thing from the above mentioned datas. Okay, this means what is our ni here? Ni is 2. I have written it capital. You can write this thing as small letters. Okay, this is our formula. It's 2 plus 4 minus 1 factorial upon here what will be ni? Ni means 2i factorial, and here it will be a 3 minus 1 factorial. This means what? This means from the numerator term you can easily check this thing, that 2 plus 4 is 6 minus 5 factorial. This is in the numerator, and in the denominator what is this? In the denominator you have 2 factorial. This means 2 times, here is a 2 factorial, 2 times 2, that is 4. This means what is the value of this thing? This is 5 into 4 into 2 into 3 into 2 into 1, and in the denominator you have, just wait, I think this is 4. I think this is 4. Sorry, this is 4. This is 3 factorial. This means 6. Okay, this means 2 times 6. What 3 2 goes with this 6, and this 4 goes with this 2, and giving rise to a 2. So the number of ways becomes 10. This is the 10 numbers of ways, that 10 ways to arrange. This means what? To arrange the 2 particles, 2 bosons. I am writing these 2 bosons in 4 energy levels. Okay, 4 energy levels. That you have 4 energy levels, and you have to you have to distribute two bosons, and what will be the number of ways? This is the microstate, nothing but this is ways. This is called ways, or this is called microstates. Okay, in the lecture of microstate and macrostate, I think you can easily calculate this thing. You know this thing. This is the what is microstate and what is number of ways. That means the number of ways will be 10. Now make the tabulation. Okay, now make the tabulation. What is our tabulation? Tabulation will look like that. You have to make 10 diagrams. 10 diagrams, because number of ways are 10. Okay, say these 10 diagrams are 1 2 3 4. This is one diagram. Okay, because there are 4 energy levels. Now you have how many energy levels? You have 4 energy levels. So you do not have to check this. These are the same energy levels. Okay, you do not have to check this thing. You just draw this thing. These are the 4 compartments that you have to distribute these 2 particles. Okay, this means now this is 1. How many you have to make? Like 10. Okay, because there are number of internal arrangements will be 10. Okay, number of internal arrangement means number of microstates. So how many diagrams you have to make? You have to make here are 1 2 1 2 3 4 5. Okay, 5. And now in the below. Okay, you are making 1 2 4 1 2 3 4 1 2 3 4. Remember that how many number of ways you have to make, the number of diagrams will be same. Okay. So these are the 10 diagrams. Now you have to distribute your 2 particle. Okay, now you have to distribute your 2 particles, which are the particles. Say initially you can easily check this thing. Oh sorry, just wait. I'm writing the energies, the corresponding energies. Okay, this state has energy minus 2e. This state has energy plus e. This state has energy plus 2e, and this is also plus 2e, because these are the 2 states which are doubly degenerate. Okay, and for all this energy level there will be same. Okay, same configuration. Okay, in this is minus 2e, this is plus e, this is plus 2e, this is plus 2e, this is plus 2e. Now you have to distribute your 2 particles. Okay, what are the 2 particles? Say initially you are giving your 2 particles on this box. Okay, this is one arrangement. This is one microstate. Okay, this is one microstate. Okay, now you are giving your 2 particles on this thing. Okay, and you are giving this your 2 particles on this, and you are giving your 2 particles on this. Okay, these are the particles, and say you can arrange like this. The first particle is in this, and the second particle is in the plus e state. You can arrange anything. So the first particle is in this, second particle is in this, and just let me arrange with similar manner, that you are giving your 2 particles like this, you are giving your 2 particles like this. Now you are giving your 2 particles, and this second particle is there, and from this say you are giving like this, and finally you are making this thing. Okay, these are the 10 microstates. These are the 10 internal arrangements that you can arrange from the number of ways. Okay, from the number, how many number of ways? Therefore you can see this is the first number of ways. This is one way, this is one microstate, this is another microstate, and so on. Okay, so what is the energy of the first microstate? Energy of the first microstate is what? Energy, I'm writing energy with black ink. Okay, energy of the first microstate will be what? 2 particle is in minus 2 state. Okay, this is not the tabulation part. Okay, I'm sorry, this is not the tabulation, this is the energy diagram part. Okay, energy diagram. minus 2e. The energy of this thing will be what? The two particles, there are two particles. Each of the particles are having energy minus 2e. Therefore, the total energy will be what? Minus 2e minus 2e. That means minus 4e. What will be the energy of the second microstate? Say this is microstate 1, this is microstate 2. Okay, therefore what will be the energy? This is energy plus e energy state. There are two particles in plus e, therefore total energy will be 2e. In this case, these two particles are in energy state, I think, plus 2e. Therefore 2 times 2e, that means 2e plus 2e, that means 4e. And in this case there will be 4e. Okay, because the very upper layer is also the 2e energy state, which is the 1 degeneracy, okay, of the plus 2e energy state. Therefore, what is the energy of this thing? What is the energy of the fifth microstate? See, microstate 3, this is the microstate 4, this is the microstate 5. Okay, this is the how much this is minus 2e plus e, because this particle has energy minus 2e and this particle has energy is e. Therefore, what will be the total energy in this case? Will be minus 2e, minus e, sorry. What is the, this is microstate 6, this is microstate 6. What is the energy of the microstate 6? This is e plus 2e, this means 3e. Here it is 2e plus 2e, I think it is 4e. Here it is I think 0. Okay, this is important thing to remember, that energy comes 0 also. And this is, what is the energy of this thing? This is 3, and this is what? This is also 0. So how many energies you are getting? That you are getting, now make the tabulation. Okay, now make the tabulation. You are getting 0 energy for how many microstates? For 2 microstates. This is microstate 7, this is microstate 8, this is microstate 9, this is microstate 10. Okay. In case of microstate 8, you are getting energy 0, and in case of microstate 10, you are getting energy. Therefore, how many microstates? How many microstates? It is 2. And energy is what? 0. Therefore, two states having same energy. Therefore, I am writing this as degeneracy. Okay, this is Gi. Okay, this is Ei. There are two states, there are two microstates having energy 0. Okay, this means 2 microstates means what? This means these are degenerate states having energy same, means what? Means degenerate states. Therefore, now you have next energy is what? 2e. Suppose 2 is what? 1 2e, another 2e. Is there any 1 2e? No, there is one single state which is having energy 2e. Now energy is say 3e. How many are them carrying energy 3e? There are 2 energy states, no more. Okay, so 3 is what? 2. Okay, these are the degenerate states number. Now what is this? 4e. 4e is, how many of them are 4e? This is 4e, this 0 has completed. This is 4e, 1 4e, 2 4e, 3 4e. Okay, these are 3, there are 3 4e's. Okay, and now you have another energy, say 4e 4e. There is a minus 4e and there is a minus e. Minus 4e has one state, minus e has one state. Okay, this energy has minus 4e, and this is 1, and minus e, this is also 1. Okay, now from this is the great big tabulation part. Okay, this is the tabulation. So write down the partition function. Now the partition function. Okay, what is the partition function of this thing? The partition function, I think you know what is the partition function formula. That is partition, canonical partition function. Okay, this is canonical, not grand canonical or micro canonical. Okay, this is canonical partition. The partition function is given by summation of gi e to the power minus beta ei. Okay, this is what is our gi, how, what is our gi in case of energy zero. This is what, this is, I can write this thing g1 e to the power minus beta e1, say g2 e to the power minus beta e2, g3 e to the power minus beta e3, g4 e to the power minus beta e4, and here it is 1 2 3 4 5 6 states. Okay, therefore you have to write 6 energy levels. That means g5 e to the power minus beta e5, and here it is a g6 e to the power minus beta e6. Okay, that means now put the g from this. G is what? G is 2 for energy state 0. Therefore, from the first term, what you can write? That is 2 e to the power 0, because E1 is what? E1 is 0. Plus G2 is what? Now write this thing G2. G2 is this one. This is 1. An energy level for 2E. So what you have to write? That 1 e to the power minus beta into 2E. Now put this thing G3. G3 is what? This is 2 e to the power minus beta into 3E plus, I think here it is. Okay, this is 3 e to the power minus beta into 4E plus, in from this thing 1 e to the power plus beta 4E. Why I am writing this plus? Because the formula is minus beta E, and you have to, this is what? This is in our case minus 4E. This minus goes with this minus and make it plus. Okay, so this is, and the last term is what? 1 e to the power beta E. This is our partition function. This is our canonical partition function. Simplify this thing. Canonical partition function, canonical. I am writing this CPF. Okay, this is what? 2 e to the power 0 means 2. 1 e to the power minus 2 beta E. Well, not writing this one. Okay. Plus e to the power minus 3 beta E plus 3 e to the power, I think this is 2, there comes a 2, 3 e to the power minus 4 beta E plus e to the power 4 beta E, and very last term is e to the power minus beta E. Am I correct? And the last term, I think, no, I am not correct on the last term. There will be a plus sign. Okay, because the energy is negative, and there is a general negative formula. Okay, this is the partition function. Okay, this is the partition function. Okay, by this way we calculate partition functions. Okay, this is the required partition function. In the next lecture we will be discussing on some special techniques of finding probability for a particular energy level, and we will do some interesting problems. Okay, now take a homework and give me the answer on the comment box or whatever it is on WhatsApp or Telegram. Okay, say question. I am giving a question. So it is 2 fermions are distributed in energy levels 0 and E, in which E energy level has degeneracy 2 and the 0 energy level has degeneracy 1, that is non-degenerate. Is non-degenerate. Okay, so you have to calculate the partition function. Calculate the partition function for this formula. Okay, this is all. So thank you for being with us. Hit like button, okay, and share among your friends and subscribe the channel. Okay, so thank you.